So now we get to the meat of the chapter. How can we determine if an argument is valid or not? And I've got an example of an argument here for us to think about. The first two parts are called the premises, and the last part is called the conclusion. Right, and the way we can kind of tell, there can be more than two premises, right? The way we can tell where the premises end and the conclusion starts is in English, we're usually looking for a word like therefore, right? That marks the beginning of the conclusion section of the argument. Now, in this case, the first statement tells us that if Spot is a dog, then we can be certain that he goes out and runs. The second statement confirms that Spot is, in fact, a dog, so it must follow that therefore he does, in fact, go out and run. Okay, so this is a valid argument, right? And it's a relatively straightforward example, but that we can kind of think through on our own. But that also makes it a good example for us to start thinking about how we can translate arguments into a symbolic form that we can evaluate using our logical tools. So let me get myself some space here. All right, so our first step is going to be to translate each statement into a symbolic form. So I'll start by letting P be Spot is the dog, and Q will be then he runs. Okay, so that makes the first premise P implies Q. The second statement is just P. And the third statement, the conclusion, is Q. Right, now notice what I'm going to do. I'm going to add a line here. Right, and the line is the math way of separating the premises from the conclusion. It's taking the place of that therefore in the English statement. Okay, now the next step is to translate this into a single statement, single compound statement, that we can write or create a truth table for. And to do that, what I'm going to do is I'll combine the two premises here with and. So it's going to be P implies Q and Q, right? And the therefore, or the line here, becomes a conditional statement. And then I've got the conclusion. Excuse me, this should have been a P, the second premise. Okay, there you go, right? So that's what I'm going to write a truth table for. Now, you want to kind of generalize this a little bit. The way this works is if premise 1 and premise 2, then the conclusion. All right, so let's think about a truth table, right? Just like we've always done, right? I've written out the complete compound statement here. Each part gets its own column, and I've got the two inputs, the P and the Q, over here. So just like I always have been doing, I'm going to write in all the combinations of true and false here. Then I'm going to copy them over, right? So I've got two P columns over here on the right. Those are both going to get true, true, false, false. And I have two Q columns. Those are going to get true, false, true, false, and the same thing over here. Okay, so what comes next? Right, well, remember, parentheses first. Right, so first I'm going to do this implication. And you remember how that one works. That one is only false when I have a T and then an F. So this is the only row that's going to get a false. Okay, good. So now we're done with this column and this column. And this middle column here is now kind of the simplified version of the entire parentheses. Okay, so next I'm going to do this and, right? And I'm going to use this column and this column. And remember, think now, and is true only when both of the two input values are true. So I've got a true and a true here on the first row. And that's it. Every other row has at least one F. So those will all be false. Okay, now again, I can get rid of these two rows, or columns. And now we're almost done. I'm going to do this implication here using this column and this column. And again, right, I'm looking for, it's an arrow, right, it's an implication, so I'm looking for a T and an F. If I have a T and an F, it's going to get a false. Everything else gets a true. And I don't have a T and an F, right? I don't have a T and an F, so everything is going to get a true. And that's what I'm looking for, right? First, remember, this is our final result. You notice that I've gotten all truths. This is a tautology. That's what we're looking for in a valid argument. A valid argument is one that is always true regardless of the input. So my conclusion here, my logical mathematical conclusion, matches our conclusion from kind of thinking through the situation. This is a valid argument. All right, so I've summarized the process here, right? So a lot of people like to have lists of steps, right? Step number one is make a truth table with separate columns for each premise and the conclusion. We put an and between the premises and a conditional between the premises and the conclusion. In other words, we break the English statement down this way, and then we've got the and the then. That's what our logical statement is going to look like. Step number two, complete the truth table. Step number three is come to our final conclusion. If we have all T's, if the argument, if the big compound statement is a tautology, the argument is valid. Otherwise, it isn't. We don't have to go all the way to being a contradiction to be invalid. All it takes is one row that comes out to false, and we have an invalid argument. Okay. So we're going next. Well, in the next lecture, we're going to look at some more examples. We're going to work through a couple more of these and see examples of both valid and invalid arguments.